Hi everyone. So we're looking at this example here. So we've got a springbok antelope that's startled, and it leaps straight up into the air. The antelope goes into a crouch to perform this leap. It then extends its legs forcefully, accelerating at 35 meters per second squared. So sorry, there's a little typo there. For 0.7 meters as its legs straighten. Legs fully extended, it leaves the ground and rises into the air. At what speed does the antelope leave the ground, and how high does it go? Alright, so let's focus on the first part here. At what speed does the antelope leave the ground? So what we're interested in here is the antelope going from its crouched position to its, legs fully extended position. So it has not yet left the ground. So sketching, right, we've got the floor here. We've got the first situation where the antelope is crouched. So there's my crouched antelope. And then we've got the situation, and I'm going to draw it off to the right here, even though it should be drawn on top of it. That would just be confusing to look at. So then we've got the antelope with its legs fully extended. So writing down our kinematic variables, what we know and what we don't know. So let's see. So this first situation, I'll call my initial. So x not at this spot. I'm going to say that's a height of 0. And when it's crouched, it's not yet moving, so its speed is 0. And let's see, when its legs are fully extended, that we're told is a height of 0.7 meters. So based on me calling that a positive 0.7 meters, I am implying that I'm calling upwards my positive x direction. And we want to find the speed of which it leaves the ground. So that's that speed right there. And let's see, any other information we know? We don't know the time. So the time it takes to do this is unknown, but we do know the acceleration at which it moves its legs. And that's 35 meters per second squared. And that's going to be positive because it goes from not moving to moving, moving upward, which is my positive direction. So acceleration has to be positive. All right, so since we're solving for velocity and we don't know time, I'm going to use the no time equation. So that tells us that our final velocity squared is our initial velocity squared plus 2a x minus x naught. Alright, so here's just the typical kinematic problem. So plugging in what we know in terms of zeros, we know we start at rest and that we start at 0 height. So then this tells us, simplifies to 2 times the acceleration times x. So then all I need to do on both sides is take a square root. So plugging in numbers, we have 2 times our acceleration times our height of 0.7 meters. Giving us a value, I just have 7 meters per second written here. I think I was being kind of sloppy here with significant figures, but I'm just going to roll with it. Ideally, we'd probably want to include, I guess, just one sig fig, because 0.7 meters is just one significant figure, so that must be why I did that. Alright, and since it's asking for speed, right, speed does not have a direction, so we do not need to include direction. If this asks for what velocity the antelope left the ground with, that'd be 7 meters per second upward. Alright, so part B, how high does the antelope go? Let me actually scroll down a bit here. Whoops. So now we're dealing with the part of the problem where the antelope is in the air. In fact, we're going to be dealing with the part of the problem where the antelope is in free fall. So just be careful, we cannot call our initial position when the antelope is fully crouched and not moving yet, and our final position some other point during the free fall process. And the reason for that is because the acceleration is different between those two situations. Whenever we're dealing with kinematics, we want to break the problem into chunks in which the acceleration is constant in each chunk. All right. Sorry guys, I have a little bit of a runny nose just because I just ate something spicy for lunch. All right. So let's see. So here's sketching out what we've got. We've got our antelope that's we're dealing with the part where its legs are fully stretched out. So basically, the point of which I called my final location, part A, is now my initial situation. And then the question is, what should we call our final location? Now, since we want to know how high it goes up, let's call our final location its peak and its trajectory. So its peak and its jump. All right. So our initial location, let's call that a height of 0. Now we'll have to keep that in mind just for the sake of problem solving. I think it'll be easier if we call this height 0. But we'll just have to keep in mind that what we're calling 0 here is actually 0.7 meters off the ground. Anyway, so we'll call that initial height 0. We know that the initial speed here we just found is 7 meters per second. We want to know how high we end up. So that up there is a question mark. Let's see, the speed at that spot. Ooh, we might think we don't know that, but we know that this is an object in free fall and we're dealing with its peak. And again, 1D motion. This antelope's just moving straight up and down. So at the peak, that speed is 0, right? Because that's where the antelope is changing its direction. So its speed has to be 0. And then our other kinematic variables is time. All right, so that's kind of for both of them. Well, time we don't know. That's what we're trying to solve for. And then finally, the last thing would be acceleration. And our acceleration here, just to be consistent, I'm still going to call upward positive, my positive x. So acceleration, well now our antelope is in free fall, so it's free fall acceleration, and since upward is positive, we're calling this negative g. So that's going to be negative 9.8 meters per second squared. All right. So we're solving for time. I'm sorry guys, I read the problem wrong. We're not solving for time. Time is unknown, and I'm not circling that. It doesn't ask us how high it goes. We're solving for its final position. So since we don't know time, let's use the no time equation. Again, so same equation. That we used before. Plugging in 0 values, looking at our knowns and unknowns. Our final speed is 0, and we're saying our initial position is 0. So we have 0 is equal to our initial velocity squared plus 2 times the acceleration times our final position. So rearranging this, and for position gives us negative initial velocity squared over 2 times our acceleration. Where at first we might be a little bit concerned because looking at this expression, we have an equation for position, but we have a negative sign here. So we might think, well, this equation will give us a position that's negative, even though we're calling upward positive, so we expect our final answer to be positive. But just remember, acceleration is negative g, so we're going to be plugging in a negative value in the denominator, so those negatives will cancel. So plugging in numbers, we have a negative times our quantity of 7 meters per second squared. So careful, that negative is outside our squared. Times 2 times our negative, and rather than using 10, again, when I computed this, I used 9.8 meters per second squared. So the negatives cancel, which is great. And doing that math, I get about 2.5 meters. So I'm going to go one extra sig fig here. Oh, why am I boxing this? Because we're not done. So our antelope reaches a height of 2.5 meters, but that's from its legs being completely stretched out. So we have to take that 2.5 meters and add its initial height of 0.7 meters, giving us 3.2 meters. Now, something I just want to mention before we finish the problem, if we were solving for time, another typical type of question asked for this might be for how long is the antelope in the air? Right? Well, this problem doesn't ask for it. There's a couple ways you could solve this, right? You could solve that by calling the initial location of the antelope, let's say, kind of like we did in part B here, where its legs are completely stretched out. And then the final, we have kind of two options, right? We could call the final location when it reaches back to the ground. So kind of drawn basically the same, but now its velocity would be negative as opposed to positive, and that's fine. So then we can solve for a time, and that'd be what's known as the hang time, the time in which the antelope is in free fall. Another way we could solve it, which usually would be quicker and easier to do, would be to call, again, just like we did in part B, call the peak of its jump the final location. And you can solve for the time for it to reach from its initial to its peak. And then use symmetry to realize, well, then the total amount of time then would be double that, because it's going to take the same amount of time for it to reach to its peak than it's going to take from its reach to its peak back to the ground. All right, so I hope that was helpful, and have fun solving physics problems.